All right, let's move into section 2. Here we will shift from IT to industrial control systems. We will start with an overview of ICS and OT and then look at their architectures and to see how the different layers and components fit together in the industrial control systems. And then we will also individually explore some of the common components that you find across industries, such as PLCs, HMIs, SCADA, DCS, sensors, actuators. So we will explore and talk about, maybe one slide each component. We will do that because these components are the backbone of OT systems, whether you are in power, petroleum, or manufacturing. These are the components in the industrial control system that you will find common. With that, then let's start with our industrial control system overview. Now that we are entering the world of OT systems, let's start by looking at industrial control systems or ICS. So, ICS are systems that are designed to control the physical devices in industrial environments. And you will find them everywhere on factory floors, in power plants, in utilities, in oil refineries. So, basically, any industry where physical processes must be automated and kept reliable. And with ICS, the operators, they can manage things like conveyor belts, turbines, robots, and flow systems. And unlike IT systems that mainly deal with data, ICS systems, they directly interact with the physical world. That means if something goes wrong with ICS, it doesn't just cause data loss, but it will cause you production stops, equipment damage, or even human safety risk. So in ICS, the top priorities are always safety and availability. Now, ICS is really an umbrella term that covers different technologies under it. So the industrial control systems, they will have different solutions under them using which the operators can control the physical devices on the shop floor. But mostly, there are these two categories that you will find for industrial control systems. And for a general understanding, studying these two common categories is enough. And these two common categories are distributed control systems and SCADA systems. So, distributed control systems are systems that control processes within a single plant or local area, and supervisory control and data acquisition systems, they are the systems that monitor and control processes that are spread across multiple geographically separated sites. So, for a general understanding, if you study these two systems, that is enough in OT security because mostly you will find these are the only two systems that you will see in industrial control systems. So, no matter which industry you go into, whether it's power, oil and gas, utilities, or manufacturing, you will almost always find one of these two solutions being used. And inside both SCADA and DCS setups, you will find some common familiar set of devices across industries, devices such as PLCs, RTUs, controllers, sensors, actuators, and HMIs. These devices form the foundation, they are the backbone of industrial automation, and they are common across industries. And one more thing to notice here about ICS is that these industrial control systems, they don't exist in isolation. They are a part of a bigger world we called operational technology or OT. And in the next slide, then we will connect how ICS and OT connect with each other, how they fit together, because very often you will find the OT and ICS terms used interchangeably with each other. ICS systems or OT systems, ICS security or OT security. So on the next slide, we will explore how they fit together. So another important umbrella term you will often hear is operational technology or OT. And OT includes not only industrial control systems, but also some traditional IT systems that are needed to make sure that the ICS devices can communicate with each other. So if you look at this figure, you will see the relationship more closely. Operational technology is the bigger environment, and inside it, we have ICS as a subset of OT. And within ICS, there are other systems like distributed control systems and SCADA systems, and some devices like PLCs that overlap between the two systems, meaning that they support both type of DCS and SCADA systems. So in practice, OT environments often involve multiple systems working together, including the ICS and the traditional IT systems. And securing OT then, it isn't just about protecting the ICS in isolation. It's also about understanding the relationship between the traditional IT systems and the industrial control systems and some of the components that overlap between the industrial control systems like PLCs. So think about it like this, like ICS devices, they rely on traditional IT components like network cables, switches, servers, and workstations. So for example, your SCADA system, your SCADA software might be running on a Windows server or Windows workstations. That means the underlying IT systems are also part of the bigger OT picture. So when we talk about OT security, the first step is knowing which components and systems fall under this umbrella and how they interact with each other. Only then we can design effective security around them. So on the next slide now, we will see some of the devices that are found in the OT environment and then which are the devices that are the most common and seen in every OT environment. So now when we step into an OT or ICS environment, we see these wide variety of devices in use. So these range from PLCs and HMIs to industrial workstations, reporting servers, temperature sensors, remote I/O controllers, and even CNC machines or power meters. And as technology is evolving, the lines between these devices is becoming more and more blurred because many modern devices now combine a lot of features into them that were once separate. Now, all these many types of devices that you see in the OT environment, they will almost always include these three components: PLCs, HMIs, and data historians. These form the backbone, they are the foundation of most industrial control systems, and they play a critical role in how operations are monitored and controlled. Now, you don't need to memorize every single device on this slide that I'm showing you in order to secure an OT environment, but what really matters is developing a familiarity with these devices. Because once you know what they are and the role they play, you can better understand how ICS works in practice and how OT systems intertwine with IT systems in the real world. So that's all on this slide now. In the next slides, let's take a closer look at some of the most common and critical devices that we see in the industrial control systems, that is HMIs, PLCs, and data historians. And let's see what they do and where do they fit into an ICS architecture. Now, let's talk about one of the most important building blocks of industrial automation, the programmable logic controller, or PLC. PLCs are specialized computers that are designed to control electromechanical processes, such as assembly lines, conveyor belts, robotic arms, and other industrial machinery. So the idea is simple. You program a PLC with a set of instructions, and it executes those instructions quickly and reliably to control physical devices. For example, you could program a PLC to open or close valves, start or stop motors, or read sensor values and then trigger an action. So traditionally, PLCs, they communicated with these devices, these field devices, using serial protocols like RS-232. But today, newer PLCs, they often support protocols like Modbus or Ethernet IP. And in our lab section, in section 8, I will show you how we will exploit this Modbus protocol and manipulate the PLC. Now, even though the newer PLCs, they support these different communication protocols, there is no universal communication standard for PLCs, which then makes them integrating and securing more complex. And another unique aspect of PLCs that creates security issues is their life cycle. So unlike IT devices, which are upgraded frequently, PLCs are designed to run for years, sometimes even decades, without being replaced. And in many environments, it's not unusual to find PLCs that are 10 or even 20 years old and still running some critical processes. And that longevity, it creates security challenges because older PLCs may lack modern security features, they may use default passwords, or they may have no authentication at all, and rarely they will receive any patches or updates. So from a security perspective, this is important because some PLC networks are completely isolated to be protected from external threats, but others are on network. They are enabled, network enabled. And if these PLCs are not properly managed, they can pose serious risks. So an attacker who compromises a PLC can directly disrupt physical processes. They can cause downtime, damage, or even safety hazards for humans. So, in short, PLCs are the brains behind industrial automation. They are incredibly powerful, but also they come with their unique security challenges. And that makes them a critical focus area when you are focusing on OT environments. When you are focusing on the security of OT environments, PLCs is something you should implement stricter controls and make sure that if they are network enabled, if they are on the network, then they should be patched, they should be properly segmented, and they should be running the newer firmwares. Now let's talk about a human machine interface, or HMI. So as the name suggests, it's an interface that allows a human to talk with the machine. So an HMI is essentially the operator's window into an industrial control system. Using the HMI, the operator can control, manage, monitor the industrial control system that are put in place to automate the physical processes. So technically, it's usually just a workstation running some proprietary software that allows the operators to monitor and control ICS processes. What makes HMIs powerful is their visualization capacity. HMIs display dashboards and schematics for real-time monitoring, showing values from sensors, alarms, and even controls that lets the operators start or stop processes. For example, as I'm showing you a figure here, this HMI is displaying some tank levels in a fuel distribution system. So operators here can open or close valves. They can activate pumps directly through this interface. HMIs, they also provide some kind of alarming system. So they are connected to sensors, and sensors can trigger alerts if pressure, temperature, or capacity thresholds are exceeded. And in many cases, HMIs may even include some automation features that directly instruct the PLCs to take corrective actions, such as shutting down the pumps or tripping breakers if they get some kind of data from the sensors that there are some unsafe conditions that are arising. And the safety aspect is prioritized so strongly that it often outweighs security considerations. And that is where the challenge lies. Because technically, securing an HMI is much the same as securing any other IT workstation. You could add EDR tools, mandate strong authentication, conduct vulnerability scans, penetration testings, or enforce unique credentials for each user. But in OT environments, things are not that straightforward. Because HMIs are mission critical systems, any disruption can cause downtime, unsafe conditions, or even physical harm to humans. That is why safety is of paramount importance in OT. And imagine if you have enforced strong authentication and unique credentials for each user, each operator who will be standing on the HMI, who will be managing the control using the HMI. Imagine if an emergency occurs, but this logged in user has stepped away on a break and the HMI is locked due to a security control. Then the consequences could be severe, right? That is why the OT staff are often resistant to traditional IT security measures. And this mission critical nature of these systems, they create tension. Safety and uptime must always come first, even if that means delaying or limiting the adoption of security controls. And as a result, securing HMI then requires a careful balance between strong cybersecurity practices and the operational realities of industrial environments. So that's all on this slide. See you in the next one. Now let's talk about data historians. So a data historian is like a specialized data repository that is used in industrial control systems. Just like you have database servers on the IT side, similarly, you have data historians on the OT side in the ICS world that capture all the data about the industrial control systems. They will store values like sensor values, alarms, commands, and these all are stored within the data historians with precise timestamps. So data historians, they typically collect data from ICS devices such as PLCs and HMIs. And data historians are also sometimes embedded within HMIs, or they can be separately, installed on separate servers if they are supposed to collect a lot of data and share with other systems. So, one of the key roles of data historians is their communication with the enterprise IT systems. So a data historian doesn't just store the data that is provided to it, but it also processes this data and provides it to the IT layer of the organization, like accounting, ERP, and planning softwares. It might provide all those values there for reporting and planning and execution purpose. So this constant need to bridge the OT and the IT world, this is what makes the data historian both valuable and a potential security risk. Because of this dual role, the best practice is to put a data historian in a separate zone, that is a demilitarized zone with restrictive access controls, so that all communication of the data historian is just one way. I mean, from here it can collect data, store here, process here, and from here it can transfer it to the IT systems. If you don't segment the data historian like this, then you will end up creating a bridge between both the networks. So an attacker who manages to get a foothold within the IT network can quickly jump onto the data historian, and from the data historian he can jump to the ICS devices. So like this, the data historian can become a bridge for the attacker to cross from the IT world to the OT world. And mostly 90% of threats to the OT network, they arise from the IT world. So the best practice is to put a data historian and all other dual home servers that are going to talk to both IT and OT devices, to put them into a separate zone. Now, we will talk in detail about this zoning and segmentation much in detail when we go into section 6, where we will be talking about ICS security fundamentals. And one of the big topics that we are discussing for network security is the segmentation of the IT and the OT network and the OT network. So we will look at this much in detail. All right, that's all for now on this slide. See you in the next one. Now let's come back to the two industrial control system solutions that we spoke when we started this section. That is, the industrial control system is usually categorized into two categories: distributed control systems and SCADA systems. In that, let's first look at distributed control systems. So on the screen here, I'm showing you a general layout of the distributed control system. It is a layered system. As you can see here, it has 3 layers. So a distributed control system is essentially a network of control devices that manage localized industrial processes. The word localized is important here because these systems do not manage, some different site or geographically different locations, but it's all within the same location. And you will commonly see these type of systems in power plants, oil refineries, and manufacturing plants, where precision and local coordination are critical. And from this general system layout, think of DCS as a hierarchical system. At the bottom layer, you have field controllers and PLCs handling direct control of equipment and instruments. And then above them in higher layers, you have the supervisory computers, operator workstations that can be used to oversee and coordinate operations across the plant. This layered approach allows the plant to run multiple production lines in a concerted and efficient way. And as I said earlier, that DCS is designed to control closely located physical processes within the same plant. Because of this localized focus, DCS was not optimized for wide area communications, unlike SCADA systems, which are built for more distributed environments. So historically, DCS relied on proprietary communication protocols. This was done intentionally as it gave a level of physical and protocol security. But this thinking that if everything stays within the same plant and runs on custom protocols, then the external threats would find it harder to interfere. This thinking is facing a lot of challenges now because this design made sense, for earlier years. Many years ago, this design philosophy made sense, but now, as you are seeing more and more IT OT convergence as times are changing with technological advancements and increasing IT OT convergence, the line between DCS and SCADA systems is becoming more and more blurred. So now even DCS systems, modern DCS systems are coming with features where you can control operations at a different site using a DCS. So, the years ago there was a clear line between DCS and SCADA system, that SCADA was used for distributed environments, wide area communications, remote site supervisory and control, and DCS was more used in the localized environment. But now, with the IT OT convergence, with a lot of IT information technology penetrating the OT world, this line is becoming blurred, and more DCS systems are also now getting exposed to the IT layer, and modern plants are now integrating both worlds to bring efficiency. Now, while this brings efficiency, but also this increases the attack surface if the security of DCS systems is not carefully considered. So the idea of this slide was to give you an overview of the distributed control systems, which are commonly seen in the ICS world. On the next slide, then, let's talk about SCADA. Now, let's talk about supervisory control and data acquisition, or SCADA systems. So while distributed control systems, or DCS, are best suited for local plant level processes, SCADA systems were designed to manage and control industrial operations that extend across large geographic areas. Think of power grids, oil pipelines, water treatment facilities, or telecommunication networks. These are the common use cases for SCADA. So a SCADA architecture generally consists of 3 to 4 main components. So here on the screen, on the slide, I'm showing you the general layout of the SCADA system, where you have these endpoints in the form of remote transmission units and PLCs, PLC controllers, which collect field data and control some devices, and then they feed it back to this backend servers that are sitting here. So here I'm showing you both the HMI plus the backend server that is getting this data, and this communications equipment is making it possible for the data to be transmitted from the remote sites to the backend server and to the HMI. And the HMI will allow the operators to visualize processes and issue control commands to these field devices. Now, one of the biggest advantages of SCADA is that it enables remote monitoring and control. So operators sitting in a centralized control center can send commands across vast distances to open valves, close switches, or adjust system performance in real time. So traditionally, SCADA systems, they relied on proprietary communication protocols and radio links. This was the legacy. For many years, these older systems were considered secure because the protocols were obscure and required specialized equipment to exploit it. But this sense of security has led to a lack of effective security controls in many legacy SCADA systems. Now, modern SCADA, however, is increasingly converging with IP-based communication protocols. So while this makes it easier for integration with enterprise networks, it also introduces new cybersecurity challenges. And legacy systems that haven't been upgraded can become highly vulnerable when connected to modern networks. So, now with IT OT convergence, digitalization, digital revolutions, AI revolution, Industry 4.0, more and more SCADA, the organizations want to connect to their enterprise IT layer in order to, maybe do some kind of data analytics, optimize, some production, improve efficiency, visibility, all those kind of use cases. And this is requiring then SCADA to communicate on IT protocols, typical IP-based communication protocols. And till the time your SCADA was old, it was communicating on legacy protocols. It was isolated, not connected to IT layer. It was safe. But now, with SCADA systems getting integrated into the IT layer, enterprise layer of the organizations, and talking on typical IT, communication protocols like IP-based communication protocols for easier integration, then this is increasing the attack surface of SCADA. Now you no longer require to talk on proprietary communication industrial protocols. Now any attacker gaining a foothold in the IT network, from there they can exploit the SCADA and create a lot of problems for the ICS world, for the OT world. So when we think about SCADA, we should remember it's all about remote monitoring and control over large areas. But at the same time, you should assess the SCADA system if it is talking to some IP-based communication protocols, if it is not isolated, if it is integrated into the IT layer for several use cases, then it requires careful attention to secure the communications and do the system hardening. All right, then with that, we have ended our section 2, where we have looked at different components. Now on the next slide, let's do a small summary before we end this section. So this brings us to the end of section 2. So in this section, we focused on understanding the architecture of industrial control systems and the common devices that make them work. We looked at critical and common components that you usually find in industrial control systems, no matter which industry. So we looked at devices such as PLCs, HMIs, data historians, DCS, and SCADA. These are the 5 components and 5 devices, or 3 devices and 2 systems that you will usually see in any industry. And we discussed their roles, what they do, what are they used for. For example, PLC is used as a brain. It's like a brain. HMI is used for interacting with the machine world. Data historian stores data. So all this we discussed, and we discussed their vulnerabilities as well. How with advancements in technologies, their efficiency is improving, but at the same time, their attack surface and vulnerabilities and risks are also increasing. We discussed that. And then very, very important, we took an introduction of the term operational technology, or OT. We got clarity on it. Remember, ICS is actually a subset of OT. So the ICS system is actually a subset of the OT system, because OT includes the complete comprehensive view. It includes IT systems that are supporting the ICS environment for their communication and networking, and plus the ICS system. So we got clarity on this, that operational technology includes both. It is important to recognize this relationship, knowing which devices are involved and how these systems are interdependent and architected, because this foundation will then help you build a stronger OT security strategy. So with that, then let's move on to section 3, where we will shift gears. Here we will start looking at how information flows in OT networks. Comparing it with the IT networks, we will introduce the Purdue model, that is kind of the gold standard, or was the gold standard for knowing how information flows in a hierarchical manner in the OT environment.